So, as Ekkehard said, we have a challenge on our hands. We have a lot of molecules that have a lot of promise, but aren't getting to where they have to be. And that's stopping them becoming attractive and viable medicines. One on the market, and antisense has been on the market for 30 years now, but only one's got there. So that's the challenge. We have put together our plan, and it's in your books. And I'm not going to read word for word what's in the book, because you can read, I know that. But what I want to do is take you through the background and why we think these are important and why we're stressing these targets. This is the suggested architecture. IMI have clearly stated that if you guys have other ideas we haven't thought of, please come forward and let us know. This is our suggestions, and this is what we're stressing within this project. Firstly is understanding the mechanism of crossing biological barriers. Every drug we give must go across a biological barrier. Unless we're really lucky and the target we have is right on the surface of the body, it's going to have to cross some kind of biological barrier, membrane. And as Ekkehard said, the body's had millions of years of evolution to stop it doing that. Once it gets across that barrier, we need to work out the cellular uptake. And these are two different things, and I'm going to explain that in more detail in a minute. But there is getting to the cell and then getting into the right part of the cell to do the work. The third one then is, once we've understood all that, is to try and work out how we exploit that with novel ideas. And again, I want to stress novel here. There's a lot of companies out there and a lot of academic groups out there who have been trying with different formulations and different ways of doing this, but what we're looking for is the next generation of that. I think if we just try and repeat what other people have done, we're going to make the same mistakes and get the same poor delivery. We have to get better than that to make sure we have the next generation of delivery systems. Once we've done all that, we must have something that can go into the clinic eventually. There is no point in building something that will stop in the cell. It has to be preclinically tested and then clinically proven at some stage. Not necessarily during the lifetime of this project, but we must design things that are going to go to the clinic. Otherwise, it's just an exercise in clever chemistry. It's not a drug at the end of the day. We're trying to get to those patients to help them benefit from the drugs we're delivering. And then finally, there's the service side of it, databases for all our data, to make sure we accumulate all the data and accumulate it in such a way we can search it and access it, and then do project management skills as well. So these are the 6 areas that really are laid out in that briefing document. And I don't want to go through in detail what's written in the document, because as I said, you guys can read. But what I do want to do is just spend a little bit of time talking about those barriers. So if we think about our barriers to success, if we think about our target cell, here's our target cell, and it's got round it a cell membrane. And that's designed to be hydrophobic on the outside, hydrophilic in the middle, so any drug that's going to be able to get into that cell has got to cross that. Okay? And if we're lucky enough to have a drug that's topical, that's all we have to do. So the drug that's out there, the antisense out there, is injected directly into the eyeball. Okay? We can get to the retina cells by direct injection. If it's a skin product, we can do that. There's an argument that inhaled drugs are topical because they're going to the cells in the lung. They've still got to get across a lot of different mucus layers and things, but that's the target. However, not very few of our drug targets are topically accessible. So the next opportunity really is to get it into the systemic circulation by IV or subcutaneous dosing. Now that's all very well, but now you've got an extra couple more membranes. You've got the membranes of the blood vessel and the membranes of the target cell. Now if this is the liver, then we know that the blood vessel is quite leaky. It's fenestrated, we know we've got good access in the liver. If this is the brain, the blood-brain barrier is almost the opposite. It's very, very tight. So we're going to have to find a way of getting across that barrier, not just into the target cell now, but out of the systemic circulation. But once we're into the systemic circulation, of course, we end up with competition because we're competing now with all the other effects. We've got the off-target tissue that may just get our drug as well. And certainly for oligonucleotides, we know that the liver and kidney take the majority of circulating drugs. We know in antibodies, really, it just stays in circulating system. It doesn't get out of that central compartment. And likewise, you've got clearance mechanisms. So your balance may often be that only a fraction of your drug will actually reach your target if you go systemically. Okay, and then as we go one beyond that, as Ekkehard said, the joy would be oral. So if we've delivered our oral formulation that's managed to get past the acid bath of the stomach, which chews up proteins and oligos, so we formulate it in such a way it survives that route down to the enterocyte. It's now going to cross 2 lots of membranes in the enterocyte. It's got to go through the hepatic portal vein via the liver, and the liver's going to have a chomp at it as well. And really then we're in a situation where our oral drug now has to go all the way through these various compartments before it gets to our target cell. So that's why we're really keen to understand the biological barriers to that. What are the barriers from the left to the right there, from that drug going across all these different membrane systems? And last time we spoke at the IMI, I liken this to my trip today. I came from London today. I took 4 trains and walked to get to this building, and then I had to get into the building. Okay? Each one of those, be it the train from my house, the Eurostar, the train up the tube line up here, all of those require different components, different properties. And that's what we're going to have to engineer into our nanoparticle, our delivery system, to make sure that our drug ends up here and not here or in the liver or wherever it ends up. Okay? So that's biological barriers. Next, let's look at the target cell. If you think about IP dosing, we're into the hepatic portal vein as well. Okay, here is our target cell. Nice little picture we like to use. There's a lot more going on in our target cell than just the cell membrane and the nucleus, as you're aware. Okay, and we've got various targets. If our target is on the cell surface, we're laughing. All we've got to do is deliver our drug to the cell surface, and many antibody therapies are that way. This is the bread and butter of small molecule medicine. Hit a receptor on the cell surface, cause a cascade inside the cell, and you're there. But we want to get inside the cell with these drugs. That's the target for us. The first port of call really is the endosome. A lot of drugs may be targeted to the endosome if we're looking at the toll receptors for immunity or autoimmune diseases. We want to try and block those toll receptors. We're going to have to get into the endosome, and there are uptake processes to do that. But really, a lot of the oligos, and certainly some of the CERNers and the antibodies, we want to get into the cytosol. And if we're really trying hard for a small set of the antisense oligos, we want to get into the nucleus. So getting across this barrier, and the opportunity to go in the wrong direction is very high. This is where we're going to be. We could use the old-fashioned transfection method. Mix it up with lipofectamine, bang it through the front door of the cell, knock the cell membrane apart, it'll get in there. We can't do that in vivo because the cell falls apart. Very few of these lipofectamine-type, lipid-type systems will get you in and get you going all the time. Works in vitro, doesn't work in vivo. We're not interested in systems that do that. Must be able to do both. Okay? Second route is the classic sort of liposome route. Comes in via the endosomes, get phagocytosed into the endosomes. Unfortunately, we get to our target, but then we end up in the late endosome where the acid bath comes in. Our drug gets pickled in acid, it gets fried in acid, and we get very little drug out. A little drug may escape from the endosome, and that may give us some targeting to the cytosol. But it's a very, very inefficient system. That's about a 0.0001% efficient way of getting it from the drug that's here to the drug that's here. Very inefficient. Now let me put that into context. If we can make that 10 times more efficient, we can drop our dosing 10 times lower. That means 10 times less toxicity, 10 times less cost of goods, 10 times less dosing. So that's important for us.